So units, another extremely important part of IB science. So there's sort of, I guess, 7 key properties that we observe in the scientific world or in the universe. There's electric current, there's time, there's amount, meaning number of something. There's luminosity, there's mass, there's length, there's temperature. So for electric current, our symbol is going to be capital I for time, lowercase t for amount, lowercase n for luminosity, big L for mass, little m for length. Now, we could say little l, especially written in cursive here, but honestly, we don't really deal with luminosity in this IB curriculum or in beginner science that much, so oftentimes we'll just write length with a big L and sort of not deal with luminosity so that they don't overlap. Then temperature, big T. So these all have units of measurement. Usually these are defined by humans in some way to represent a specific amount. So the units for electric current is amperes or amps, time seconds, amount mole, luminosity candela, mass kilogram, length meter, temperature Kelvin. So all of these units also have a kind of 1 or 2 or 3 letter symbol that you can write quickly when you're doing equations. So for amps it's A, time S, amount mole MOL, luminosity CD, for candela mass kg, length M for meter, and temperature K for Kelvin. So I often show this to students, and then they ask, what about like area? What about volume? What about newtons for force? What about watts for power? And yes, all those things exist, but they can be expressed through SI base units in some combination. So let's look at what I mean. Well, first, metric multipliers. These are also hugely important. You probably know some of these basic things, like when you compare meters to kilometers or grams to kilograms, there's a difference of a factor of 1,000. But these are the ones that are in the IB data book that you're expected to be able to communicate and understand and express properly. So, peta, tera, giga, mega, kilo, hecto, deca, deci, centi, milli, micro, nano, pico, femto. So you can see that these powers of 10 differ by 1 in between kilo and milli. I mean, kilo to hecto is power of 10 to the power of 1, hecto to deca, 10 to the power of 1. But as you get beyond kilo and go up, we start jumping by 10 to the power of 3. And as you go smaller than milli, you start jumping by 10 to the power of minus 3 as well. So it's important to know the prefix, the abbreviation, and the value. These are in the data book. You don't have to memorize them. You just have to know how to use them properly. Now, you should also know that 1 liter, a metric unit of volume, is equal to 1 decimeter cubed. And similarly, 1 milliliter is equal to 1 centimeter cubed. I think that's also in the data book. All right. So what about non-SI base units? So the liter, as I just mentioned, has a relationship with meters, the SI base unit of length. 1 liter is the same as 1 decimeter cubed, and that is the same as 0.001 meters cubed. Now, you don't necessarily have to fully remember or understand this, because I think that this ratio is also just given in the IB chemistry data book. But you should follow this, that some scientists just decided, decimeters cubed is too difficult to say. Maybe it wasn't even scientists who decided this, maybe it was just some people. But they don't want to say decimeters cubed every time, so they're going to say 1 liter. But it is exactly the same as 1 decimeter cubed. And you can fit 1,000 decimeters cubed into 1 meter cubed. What else? Dollars. Here's a non-SI base unit. Dollars is just a human-created value for money, and it isn't directly related to any SI base units, but you'll often see it combined with other units like, I don't know, dollar per meter, and you might be asked to consider what's the cost of building a track of some length or a building of some height. You need to be able to create your own units and ratios in this way as well. Inches, often written with two little quote lines. This is the American unit of length, but this can be expressed in meters. This is 0.0254 meters. I just want to write here that this can be expressed as a ratio of 0.0254 meters per inch. And you can use that in unit conversions, for example, some of the type that we'll see later on. All right. Gallons, GAL. This is the American imperial method of volume measurement, but there exists a conversion rate to convert gallons to meters cubed as well, 0.003785 meters cubed per gallon. Degrees Celsius, written with little circle C. So this can be converted to and from Kelvin, which is an SI base unit. So degrees Celsius plus 273 or 273.15, I think, is equal to Kelvin units. Fahrenheit, again, the empirical or American way of measuring temperature. Take a look at that equation. Temperature in Kelvin equals 5/9 multiplied by the temperature in Fahrenheit plus 459.67. Wow. But there is a way to convert an SI base unit into Fahrenheit or vice versa. Joules. This is a unit of energy. You might have heard this before, or maybe this is the first time, but a unit of joule can be expressed as SI base units. It is 1 kilogram times 1 meter squared times second to the power of -2, or kilogram meter squared per second. I've written multiply with stars here. You might see that sometimes, or you might see like a little circle, or you might just see nothing at all. Just kg m squared s power of -2. All of these mean the same thing. Alright, so this brings us to something called dimensional analysis. We often have to convert between such units as these, or do calculations with them. So practice question, change 34 liters L into meter cubed. So some of you can probably just do this in your head, but as you're learning the basics of this, I recommend you write out everything, even into single steps. So 34 liter, let's convert that into decimeter cubed. We can multiply by a conversion factor, or a ratio. 1 decimeter cubed per 1 liter. And when you do that, when you have liter divided by liter, that ends up equaling 1. And these cancel out on the left. You'll be left with just 34 decimeters cubed. You multiply 34 times 1. Now that's not complete yet. Question asks for meters cubed, so on the right side of this calculation, I'll multiply that by another conversion factor, or another ratio. So 34 decimeter cubed times 0.001 meter cubed per 1 decimeter cubed. I know that there's 1,000 decimeters cubed in 1 meter cubed, so this is also true. 0.001 meter cubed per 1 decimeter cubed. So I end up multiplying 34 times 0.001. My decimeters cubed cancels out, and I'm left with units of meters cubed, 0.034. And I'll keep my two significant figures that I had in 34 liters. All right, a student ran 2.0 kilometers in 42 minutes. What was their average speed in meters per second? So you're going to need to convert kilometers into meters and minutes into seconds and divide these things. So for the first part of the calculation, kilometers into meters, you can multiply them by a conversion rate. 2.0 kilometers times 1,000 meters per 1 kilometer. We'll end up multiplying 2 by 1,000. But we need to keep our two significant figures in 2.0 kilometers. So write it in scientific notation. 2.0 times 10 to the 3 meters. Next, minutes. Multiply this by a ratio. This is not in any data books or anything, but you pull this from your mind, you know that there's a ratio of 60 seconds per 1 minute. So 42 times 60 seconds per 1 minute. Minutes cancel. We're left with 42 times 60, 2,520 seconds. And then you do kind of have to know an equation for speed, that is distance divided by time. So put your distance on top, your time on the bottom. Put those in the calculator if you need. And you'll get an answer of 0.79 meters per second. And it needs to have two significant figures. Because 2.0 kilometers and 42 minutes were our inputs for this, basically. All right. So you might say, why does 2,520 seconds have three significant figures? That's a good point, but generally I would say don't worry about cutting off significant figures too much until you reach the final part of a calculation where you have to report an answer. That's the part I have here in the green box. Until you get there, you can include a couple extra significant figures to help proper rounding throughout the process, if that makes sense. All right. So there's some dimensional analysis practice we have here. So we can look at these three practice questions. What's the mass of 25.0 milliliters of octane? Density, 0.702 gram per centimeter cubed. Then second, what's the mass of 125 milliliters of gaseous chlorine? Density, 3.16 gram per liter. And finally, convert 195.7 inches squared into meters squared. 1 inch equals 0.0254 meters. Okay, if you guys want, you can pause the video, try to answer these yourself. I also have a link here for further questions. I'll try to put in the video description if you want more. Alright, if you've tried it, I'll show the answers here. 17.6 grams for number 1, 0.395 grams for number 2, and 0.126 meters squared for number 3. But let's go show this on a whiteboard, how exactly it's done. Okay, so the first was 25.0 milliliters, and we're trying to get this into a mass. So what you generally want to do is set up a chain of conversion factors that will eliminate units you don't want and introduce units that you do want. So 25.0 milliliters times. First, I want to get this into centimeters cubed. So I know of a ratio, and that is that 1 centimeters cubed equals 1 milliliter. If I do that, my milliliter units will cancel out. So that is now equal to 25.0 centimeters cubed, but I'm not quite done yet, so I'm going to add another conversion factor to this chain, and that is the density that was given in the question. That density was 0.702 gram per centimeter cubed. When I multiply by that conversion factor, my centimeter cubed will cancel out to 1, and I'll be left with units of grams, which is what I want, a mass unit. So this is what comes out to the answer, 17.6 grams. Second question, quickly. So I have 125 milliliter. I'm trying to go to a mass again. So 125. Sorry, always write units when you can. Milliliter times some conversion factor. So my density that was given in this question was in grams per liter. So I also want my volume here to be in liters. I know of a conversion rate between milliliters and liter. So you guys might think the ratio is 1,000 milliliters per liter. While that is true, you can always flip these conversion rates or take the inverse of them. There's nothing that says you can't do that. So 1 liter per 1,000 milliliters. If I write it this way, I'll get what I want. My milliliters cancel out, I'll be left with liters. Then I can multiply by my density given in the question, 3.16 gram per liter. My liters will cancel out. So really what I'm doing is dividing this 125 by 1,000, then multiplying by 3.16, and I will get units of grams, 0.395. 3 sig figs, just like my original measurement. Alright, last one, number 3. Quite a challenge. You need a little bit of extra math knowledge perhaps to solve this, but 195.7 inches squared. And we want to bring that to meters squared, another type of area in metric units. So 195.7 inches squared. Multiply by some conversion factor. So what we have is, in the question, 1 meter per, 0.0254 meters per 1 inch. Alright, so maybe you can see that this will not quite work out. We're going to have inches squared divided by inch. I should just write this as IN to keep this consistent. But we're only going to cancel out one of these inches. We have inches squared on the left and inch in this conversion factor. That's not going to give us the proper results, so one thing that you can do is square this whole conversion factor. There's no reason you can't do this. This is not like an equation yet, so just square your conversion factor. When you do that, then inches squared will cancel out inches squared, and we actually solve two problems at once because this will make our output no longer in meters, but in meters squared. And this ends up 0.126, because what you're going to do is multiply the number 195.7 times 0.0254 squared. And we get, not meters cubed, sorry, meters squared. for the answer. Okay, so you've got to make sure the type of units cancels out and the right number, whether it's single or squared or cubed. These things have to cancel out properly and leave you with the units that your question is asking from you. All right, let's go back. So, also science, math, and communication, superscripts and subscripts. This is just a couple notes I have about how to use and understand these things. So superscripts in chemistry are usually exponents on numbers or units. For example, meter squared, kilogram cubed, 2 squared, which is 4. Usually that's what we're dealing with. One important relationship that I think you really need to know is that 1 over a number equals that number to the power of negative 1. 1 over a number squared equals that number to the power of negative 2. 1 over a number cubed equals that number to the power of negative 3, and so on. You'll see both of these representations throughout the IB science programs. So one common example is 1 gram per liter. You can express that as G per L, or GL to the power of minus 1, or G per decimeter cubed, or G decimeter cubed to the power of minus 3. All of these represent the same thing, gram per liter. You can usually choose which one you want to express your answer as, but you have to understand all of these could be written in a question as information given to you. Superscripts are also used to show electric charge on ions. We'll talk about what those are later, but Mg superscript looks like kind of to the power of 2 plus, or N superscript 3 minus. This represents electric charges on those ions. You'll often see that as well. Alright, what else? Subscripts. Subscripts in chemistry are usually describing different versions of mathematical values. So, for example, P subscript I in the bottom right. Maybe this means the initial pressure of some system. You'll compare that with the final pressure later on, PF. Or delta HF. So here again, F maybe you would think means final. It could in some contexts, but usually it's going to mean formation type of enthalpy. H is enthalpy. And there's very many different types of enthalpy. There's delta HC combustion, there's delta HF formation, there's delta H lat for lattice. There's a whole bunch of different ones, so we need these subscripts to indicate which type we are talking about. Sometimes they also represent number of atoms in a molecule in molecular formula. So for example, you guys probably know H2O, CO2, H2SO4. The numbers there are written as subscripts, smaller versions in the bottom right corner after some letter. That represents how many of that type of atom exists in that compound. Sometimes they'll also show state in brackets after a formula is written. So H2O, subscript bracket L means liquid state H2O. H2O bracket subscript G means gas, so we can indicate states this way too. Alright, a little bit of an extra note here. Percentages and decimals. So proportional fractions, these are when you make a fraction of 2 of the same thing, or 2 things with the same units. And usually when you make a fraction, that number on the top is going to be less than the total. So imagine I had 10 apples, and I set up this proportional fraction of 5 red apples. The rest are green, but I have 5 red apples over 10 total apples. So my proportional fraction here is 5 over 10. Maybe I can write that here on the slide. Okay, so maybe I had 5 over 10. apples. They have to be the same units for this to make sense. Then this number can also exist as a decimal version. 0 point some number. You can get numbers that are over 0 if you end up with x1 greater than x2, but let's just stick with fractions less than 1 for now. So 5 over 10, that's going to give us a clear decimal number of 0.500 going forever. This can also be expressed as a percentage, where you multiply that decimal number by 100% to get sort of xx.xxxx%. So this would be 50.00%, depending on how many significant figures or decimal places that you are working with. So it's really important to realize that all three of these represent the same thing and how to convert between each of them. To convert between proportional fractions, you need to use a calculator or long division. I haven't done long division in a while, so like me, you'll probably stick with your calculator. To go from decimal number to percentage, multiply by 100%. To go in the reverse of these, you do the reverse, although it's not that easy to go from a decimal number to a fraction. You kind of have to think about where that decimal number came from. Okay. Moving on. Proportionality. Very important idea about the relationship between variables or properties in a mathematical equation. So, how do we get a proportionality out of an equation? You can take any equation. Take a 3-variable example. This is one of the simplest equations. Speed equals distance divided by time, or v equals d over t. Then you need to choose 2 variables. Consider the others as a constant. So let's take speed as a variable and distance. And we're going to set time as a constant. We're not interested in what happens when time is changing. So t equals constant k. That sets up our equation now as v equals d over k. And what you want to do is factor out the variables that you're interested in. So factor out d from d over k. You'll get d times 1 over k. Alright, now to find proportionality, ignore any brackets that contain only constants. So the bracket 1 over k contains only constant values. Ignore it. And by ignore, I mean delete it. Okay? Don't write it anymore. And then change your equal sign to alpha, the Greek letter. That's the proportionality sign. So if v equals d times 1 over a constant, that means v is proportional to d. v is directly proportional to d. And so you can say that this is true. Speed is proportional to distance. Speed is proportional to distance. We'll talk about what that means in a second. But that is how you pull out proportionality from a complex equation. Well, this one is not complex. It's quite simple. But let's try with a more complicated one. Proportionality, let's consider a difficult equation. Here's, I think, Newton's law of gravity. 5 variables. Actually, one of these is a constant, but F force equals g, gravitational constant, times mass of one object times mass of another object over r squared. R is the radius or the distance between these two masses. Even if you have no idea what these are, you can still find the proportionality. Just follow my instructions. Choose 2 variables. So we'll choose f and
r.
If you choose 2 that are not immediately set up properly, like where one is on the left and then the rest of the variables are on the right, you need to rearrange the equation sometimes, but choose one that you want to be on the left of this equation, that's force here, and then another that is on the right. We can choose radius. Now, I'm interested in force and radius. I'm not really interested in G, M, or M1 or M2. So I'm going to treat G, M1, and M2 as constants. So them all multiplied together equals a constant K. Then factor out that constant, G, M1, M2. So that's factored out on the left. I'm left with 1 over R squared, also in brackets on the right. And as I've just defined, G, M1, M2 is a constant K, so I'll just combine those together into one constant K. So F equals K times 1 over R squared. Then what did I say? I said ignore K or delete it when you convert this into a proportionality. So F is proportional to 1 over R squared. K goes away. And the way that you read that is exactly that. F is proportional to 1 over R squared. So when you get good at realizing what proportionality is, you don't have to do this every time. You can just look at an equation and say, okay, I know if I set all my other variables constant, I will end up with F proportional to 1 over R squared. Probably won't take you that long to get used to pulling out proportionalities, but it's hugely important because it allows us to talk about relationships between variables quickly, and what kind of change we expect from changing some of these variables while holding the others constant. So here's a little collection of graphs I got from corbetmaths.com, but these are proportionality graphs. So when you have something that's directly proportional, like speed and distance, y proportional to x, your graph of these variables change over time is going to look linear. Okay, it's going to look like a straight line on the left here, y proportional to x. When you have y proportional to 1 over x, or one variable proportional to 1 over another variable, you're going to get what's called a hyperbola. It looks like the graph y equals 1 over x. When you have y proportional to x squared, you get a parabola. You guys studying math probably know this as a quadratic function. When you have y proportional to root x, you get sideways sort of reflected parabola. Yeah, but this is really important to predict how graphs are going to look and how relationships are going to produce results, basically. So I have a nice summary table here. When y is proportional to x, straight line, when you double x, y will also double to 2y. When you half x, y will also half to half y. What if you have y proportional to 1 over x? An alternate expression for that is y proportional to x to the power of minus 1. That produces a hyperbola graph. It looks like the graph of 1 over x squared. When you double x in this case, y halves. When you half x, y doubles. This is called inverse proportionality, also a very common type. Alright, what happens? Y proportional to x squared. That is a parabola graph, quadratic function. When you double x, y multiplies by 4, by a factor of 4 increase. When you half x, y decreases by a factor of 1/4. Alright, what about y proportional to root x? That's the same as y proportional to x to the power of 1/2. It's a kind of sideways parabola. When you double x, y increases, but not by double, actually by root 2. So that's less than double. What happens if you half x? Y decreases, but not by half, by instead root of 1/2. I might be able to go into where these come from if you're not able to see it yourself in a future video, but let me know. So y proportional to 1 over x squared, same as y proportional to x to the power of minus 2. This is a steeper hyperbola. I just mean that it's going to approach the asymptotes at a faster rate, I think. When you double x here, y decreases by a factor of 1/4. And when you half x, you get 4y as an output from this type of relationship. Okay, so these are quite important. I'd say the immediate ones that are important are the first two, direct and indirect proportionality. But anytime we see a new equation, I'll try to remember to ask what's the proportionality between several pairs of variables.
Okay, I was hoping we could finish this in 2 parts, but I think experimental uncertainties deserves its own video, so stay tuned for part 3.